So now we will discuss a new topic, and we will touch upon the reinforcement learning and Bayesian optimization. So please do not expect from this lecture something like an in-depth introduction to reinforcement learning and Bayesian optimization. So for these two topics, we can actually spend, two different courses. However, I would like you to know, at least conceptually, at maybe some higher level, what are these two concepts and what kind of algorithms we can use. And I hope that you get interested in that and you will Google by yourself and look for more complicated and more, interesting approaches to these two topics. And so let's start with reinforcement learning. So here we have, let's start with some kind of examples. So here we have a robot that learns to follow an object, and this is a video and part of research done in at the Vrije Universiteit in our group Computation Intelligence led by Gusti Iben. And you can see a tiny robot in front that it's, let's say, running away from the other object, and the other object, so-called gecko, is trained to the controller of this robot, so-called brain, is trained to look for a moving object and follow it. And as you can see, it's pretty successful. Another example that it's very, very important is to train an arm of a robot to manipulate items, right? So instead of, maybe I didn't say it, but instead of predefining, pre-coding these robots, so of course our hope is that they can learn by themselves. And here we can see on the left how it looks in simulation, and then it is trained in simulation because it's easier, of course, and then the same controller is embodied in this real arm robot or robot, and you can see that actually it's doing pretty well, right? So this is capable of manipulating these tiny objects, moving them, and so on. Another example, more maybe down to earth, is learning how to play video games. So here we have this simple, bar and a ball that needs to hit all other blocks, and the ball cannot go beyond the moving bar. And this kind of games, so-called Atari games, were started learning these Atari games has been started by DeepMind and OpenAI, where they realized that, hey, actually we can look at this simple environment, simple worlds with well predefined rules, and the question is, can we do better than human beings, right? And this is also started, I would say, very, very vivid and interesting field of research. And DeepMind is one of leading research groups in the world on this topic. So probably you've heard about AlphaGo, AlphaZero, playing StarCraft, and so on. So this is something that is interesting for many, many people, and we can even simplify, as you can see. So we go down with complexity of a problem. We can even learn to play ping pong, and then there is one bar is an agent, and the other one, let's say, is a human player. And we of course want to play to learn how to play. And we actually will focus on this simple scenario because it's very easy to grasp. We have actually two actions. We can go up or we can go down at each time step. And of course, we want to learn a controller that is able to win. And so, what do we have in this? simple game. So we have an agent, and by agent we mean, let's say, a code, a piece of code implemented, I don't know, in Python. But also there is this code contains a learning algorithm that is able to update its representation about the world, about the environment, and also is able to update its policy to take actions. And so we have an agent. It can make two actions, going up or going down at a given time step. And we have, of course, the environment, where we have some states of this environment. So where is the ball, where is the opponent, and so on. But mainly, let's say that we are focused on looking at the ball. So agent takes some action, and then environment returns a state and a partial reward, okay, or a reward in general. So this is how it goes. What is important here, and this is something different than supervised learning, for instance, is that the agent is embodied or is a part of this environment, so it has to interact with the environment so that to achieve some goal. In this case, to win the game. And we can have sequences of actions that are finished, and they give us the final reward, let's say. And in this case, it could be that we first sequence ended up with a win, the next sequence was a lose, and then the last one is a win again, right? So this is, of course, very simplified. These sequences could be shorter, longer, the number of course, actions that they can vary. And here is interesting part is that, and we see already complexity of the problem, is that a very similar set of actions, they can lead to completely different outcomes. So you see that down, up, up in one case produced a win, but in other case produced nothing, and then the agent had to move down, and then he lost. Okay, so you can see that now. I hope that you start seeing that this will be quite complex, right? Again, also if you think about the space of all possible actions taken, this is enormous, right? Especially if we have a varying number of actions. To formalize it a bit, so and I want to underline, I want to stress out that this is a very brief introduction to reinforcement learning, right? So this is very this is very specific implementation, or there are different problem formulations. This is basically problem formulation that is very simplistic, taken from a textbook, but in reality we can make it more complicated, more challenging, and so on. Okay, but let's focus on something simple. So we have in this reinforcement learning, so of course agent takes some actions using some kind of policy. We denote it by pi. It could be a deterministic policy, or it could be a probability, stochastic policy. So every time, there is some small chance of randomness that it will make a different action. Environment returns state and reward. Sometimes this state, so state must be always somehow presented to an agent, otherwise there is no interaction. However, reward is not always given. So in general, it is assumed that we have some kind of reward. Sometimes we don't have it, this partial reward. Again, this is it could be deterministic, it could be stochastic in nature, but more or less we don't have access to that. To us, it's more like a black box. And what we can maximize, and in this case, this is what we want to maximize, is the cumulative reward. Okay, where we define some discount factor gamma, and this is what we want to do. So in given state, you want to make actions that will observe what are rewards, and so in other words, the cumulative reward is what will happen in the future, where I will end up. Okay. So this is a little bit tricky, right? Because we start with in some state st, for instance s0, and then we just make an action, and then it's reward. We make another action, reward, and this is the cumulative reward according to given policy. Okay. And why this optimization is so weird and specific? So the analytical form of the objective function is rather unknown. We can only, so black box, we only have this partial information about individual decisions. And in order to get the final outcome, we need to make all decisions. So, to feel the subtlety, the difference between standard optimization and this optimization, also to feel the subtlety of this partial rewards, is that you can do you can get some positive reward gradually, but it might be that you will lose anyway in the end, because this is maybe something like harmless at this point, but it will lead to a very bad situation. So this is problematic. It's a little bit like you pick the wrong path. You want to climb a mountain, and in the beginning you follow this path that is easier, and you're climbing up slightly bit. At some point you see that there is no other way to go up. You must go back, right? So then you see that all these actions were basically wrong. And it was better to put some more effort to go this harder path, but it will at least lead us to the top. So to see the final outcome, we need to make a lot of decisions, and of course this makes it very hard, because this is something which is called a credit assignment. So which actions are to be credited for rewards, right? So in the beginning, when we have these two paths, it's hard to say. It might be even impossible, right? So this makes this very hard, because also then in some sense the stimulus to make some actions, it actually could be evaluated only in the end. Another question is about exploration against exploitation, right? Should we rather try different solutions, and then of course we spend way more time to verify whether this is good or bad, or we should rather exploit, right? Current good solutions. So let's say that when we take babies and they walk in a room, very often they make super stupid mistakes, right? But they also learn by that you cannot touch something that is hot, because then it will be painful. If they don't learn it by themselves, then can make this mistake in the future, and it could be way worse. Okay. If they learn that if it's slippery ground, so you must be careful, otherwise you can fall down, right? And so on. Another thing that it's very specific for reinforcement learning is something which is called lifelong learning, or continuous learning, or continual learning. So we would like to perform multiple tasks at the same time in a continual manner, so that we never forget what we learned. So again, if we look at babies, so babies learn to walk, to run, to rotate, in a sense, like these are these very simplistic tasks that we try to learn to teach robots. And babies do the same. They look how to rotate, how to walk, how to run. They start adapting, and they never forget any of these skills. And then they make a decision. Now I will run, and I run. Now I will rotate and see who is behind me. So this is easy. For robots, for instance, it becomes pretty difficult. So it's so this is something like brings us closer to real AI, I would say. If I even personally I believe that if we come up with a good mechanism of learning multiple tasks at the same time, without forgetting them, and only upgrading them, then we will be able to say that all right, we have a real AI machine. And today, because I would like to teach you every time some specific algorithm, or specific piece of knowledge. So I would like to finish reinforcement learning with the most simplistic so-called off-policy reinforcement learning called Q-learning algorithm. And the Q-learning algorithm is based on a very nice observation, is that if we denote by V star, so the optimal future value, we can actually we can write it as max over all actions of Q function. And what is Q function? So Q function is the recursive formula that we can define the cumulative reward. Okay. So then it turns out that we can express this cumulative reward using this Q function. I don't want to go into details how to derive it, so please Google for it maybe. This is not so extremely important. It's good that if you remember that there is something like that, and you can always come back here and you know what to look for, all right? But so please believe me that these formulas are correct. So then what we look for, because these Q values, Q functions, they are real. Real parts of this cumulative reward. Of course, we don't know them in advance, so we will try to estimate these Q functions. Okay, and how to estimate this Q function? We have this recursive formula here. So this is what we will try to do. We will try to update. Let's take a look at what is in the bracket. Okay, so we have this reward. We have this gamma, and gamma is this discount factor. We have this maximum of over all actions for given current estimate of Q in given state and given action, right? Sorry, not given action, because we maximize over all actions. Then we have minus old value, and then in front of the bracket we have plus old value, old estimate, and we have also learning rate. This is this alpha, and so these arrows are shifted a little bit. So learning rate is of course the alpha, and discount factor is gamma. Okay, and this of course works only if we have discrete states and discrete actions. So yeah, this is what I just said. And how it goes. So let's say that we have very simple scenario. We are moving in a grid, okay? And we have G, that is goal, and once we enter the goal, we are stuck there. We cannot get anything else. And if we move from one cell to the other, you see that only we'll get reward if we go from the adjacent cells next to the goal. We cannot move diagonally, we can move only left, right, up, or down. And in the middle, on the left, we see that there are these Q values for given discount. Also, we assume some discount factor. And then we also have this, so these are the skew values for given state and some action. And this V star, this is the optimal policy where we have in each cell, in each state, we know what is the expected reward, total cumulative reward, sorry. And one optimal policy, so a policy is depicted in the bottom. And how works this Q-learning algorithm, right? It is very simple. So here is a code snippet. So we initialize this Q somehow, so with zeros in the beginning. Then we define the real reward as a matrix, right? We'll read from it. Then we, of course, we select an action that maximizes Q and check the new state. So we ask the environment to get us some reward, and then we have the update of our Q table, right? So this is written down what we had on the previous slides. And this is basically that. So this is super short introduction, 20 minutes introduction to reinforcement learning. But I would like to, from you to remember about what is the reinforcement learning in general, how it's different, and also that how it's different from supervised learning, and that this is more or less about this interaction between the environment, okay? And what about Bayesian optimization? Bayesian optimization is something a little bit different. So in reinforcement learning, we have these partial rewards, and we assume that they are known in general, not always, but in general. So we assume that after every step, we see something that we are rewarded somehow, right? But this knowledge is very often unavailable. We really need to wait for the final outcome. So for instance, if we learn a robot that to achieve some goal, maybe we don't know what to do in the middle, right? Unless it achieves that, we have no idea what kind of reward we should give it, right? It's very unclear. So and also in our group we also used reinforcement learning for our robots, and it turned out that it doesn't work at all. Very often it is impossible to learn using reinforcement learning. But we can of course propose partial rewards in some arbitrary manner, right? We can come up with this, but then it becomes a part of modeling, okay, process. Very often people forget about it and they formulate the problem and they say, hey, our approach works better because we proposed these partial rewards. But then we look into the paper or into the code and you see, but come on, this was proposed only for given very particular a problem. For instance, it is not generalizable. So what's the point? It's like, it's like overfitting to the problem. And that's why also there is a very close connection between reinforcement learning and evolutionary computing, because partial reward could be understood as fitness function, all right? And the difference between these two approaches is that in reinforcement learning we try to learn maybe the reward function, we try to learn environment, we try to of course learn the policy, but in evolutionary computing sense, it's more like we run in parallel multiple simulations and we see which one gets somewhere, for instance, in quickest and is in the shortest time. And then of course we can select this population, these candidates, individuals that seem to work best, right? So far. So these are a bit different concepts in reinforcement learning. It's more about having some single model and in some sense like one individual that runs multiple times when we optimize it, right? But these days it turns out that actually these connections are very close, and evolutionary computing, as you saw in previous lectures, so they are very competitive compared to reinforcement learning, and actually it turns out that they work sometimes even better. So there is, for instance, in Google right now, there is a team that also works on evolutionary computing instead of reinforcement learning, and they get very good results. All right. So what we can do when we have optimization with unknown objective, and we assume that partial rewards are unknown, and we can only evaluate a sequence of decisions as a whole. Okay. We don't know the objective. We can only observe the outcome and the final outcome. Okay. So there's the problem of credit assignment, right? We don't know which actions in the middle led us to good scores. Okay? Because we can make some decisions, we move up, down, up, down, and we will win. And then, okay, which of these were good actions? Okay? How to deal with that? So one approach is to train a surrogate objective and include uncertainties. So we will look at our decisions, and we will try to somehow to propose a model that will generalize our decisions in a way, but also we need uncertainty. Okay. And what we can do, and here we will talk about Bayesian optimization. And Bayesian optimization is a very specific field. It is about optimizing. It is about optimizing a surrogate model. But this is the idea. We don't know the objective, but we can treat it as a random variable. Okay, now it is not maybe a vector. This is a function by itself, but we don't know what is the function. But we can assume that this is a stochastic quantity. It is random. Okay. So now what we'll do, we have some given data. So we have some x's. It could be some decision or whatever sequence. We have some x's, and we have outcomes. And we have these outcomes given by our objective. So these values are real. We don't know what is f. And we are interested in finding the posterior over the class of possible objective functions. So here we use Bayes rule or Bayes theorem to invert probabilities. In order to calculate posterior distribution over objective functions for given data, we need to calculate the likelihood of data for given function times prior distribution over functions. This is proportional to this. Of course, to get equality, we would need to divide it by P of D. But since this is not of our interest, we are interested in F's, so we can skip it. And then, once we have this posterior, we can very easily predict the value for a new point. So we have predictive distribution, so where we removed all possible functions, okay? And we can say that this is our surrogate objective. So now we know that what outcome I will get for a given point. In some sense that I got rid of, in a stochastic way, a probabilistic manner, I got rid of this random, unobserved quantity objective function, okay? So this P of y given x for given data is a distribution. So it will tell me that for some x's, I can expect some value, but with, for instance, very high uncertainty, because there was nothing like that in the past, okay? And then if I have even a sequence of actions and some sequences are similar, so then they should, maybe, it's intuitively, right? They should somehow reinforce each other and provide me lower uncertainty, okay? And we will see in a second how we can do that. All right, but how we can build a surrogate objective, right? So next thing, of course, is when I learn, right? So let's say I'm learning a robot, and I'm interested what is the next point to verify, so that I can, for instance, lower my uncertainty. So for this purpose, we use acquisition function that uses the surrogate objective, okay? So for instance, if the surrogate objective is Gaussian, then we can use the mean value and the variance to pick up the next point, okay? Right now it sounds a little bit heavy probably for you, because there are something like some integrals, Bayesian statistics is involved, objective function is random, variable, and so on. But please try to be with me for a second. I hope that once we show some examples and some plots, it will become more clear to you. Okay? But right now the idea is that we have the surrogate model, and we have acquisition function that will use this surrogate to pick next possible points, okay? To relate it again to a robot, in reinforcement learning we assume that it follows somewhere, and it will try to get these partial rewards to get reinforced, stimulated to get somewhere. But in this case it would be more like, okay, perform some actions and see what is the outcome. And then, okay, it works, but where is my higher uncertainty, for instance, if I want to explore more? Or where is the lowest uncertainty? I want to get some, for instance, confirmation or approval, disapproval of my current action. So I perform another actions and I check my outcome. And then I try to, with surrogate objective, I try to see where are these, highly rewarding places in the Y space, right? So then I use again acquisition function and I try to follow another actions. So it's more like really looking for places where the surrogate model will somehow combine information about my past actions. All right, let's try with some very simple example. We will use a non-parametric model, k-nearest neighbor. Okay, I hope you know this model. This is very easy. We have some points in our space. Then we get each point is assigned with a value. Let's say it's a regression task. So when we have a new point, we look for similar points in the space, and we just calculate average of neighbors, k neighbors. Okay. So the probability of objectives is uniform distribution, because it's something like we have every single model that is defined by these k neighbors is uniformly distributed. So posterior is also uniform. So it's actually very simple, because the surrogate simplifies to just Gaussian distribution with mean that is defined by so far observed these neighbors, and variance that is just empirical variance from my neighbors. Okay, so then it's very simple. So this is the surrogate, and of course I can use some acquisition function, for instance upper confidence bound. So the upper confidence bound tells me where to look in using the mean and variance and some scaling of variance. Okay, there are many other acquisition functions, but here I just use this. Okay, what I can do more, so I can do, for instance, I can take a non-parametric model. It's a Gaussian process. Okay, And the probability of objective is given by Gaussian processes. This is more complicated model. We'll not go into details. If you are interested, please look for it. It's just a name for now for you, but this is a very powerful model. And the great thing is that it gives us posterior distribution is Gaussian, and the surrogate surrogate objective simplifies to Gaussian again. So we can use, one more time, we can use some acquisition function, upper confidence bound or expected improvement, probability of improvement. As I said, there are different acquisition functions, and we can pick one of these to perform this Bayesian optimization. And now the example that I promised. So let's say that we have here, there are x's, there are y's, okay? And we want to learn a distribution over objective function. Let's say that this black curve is the real one. And here is our surrogate model, you see? So when we have observation, so there's no uncertainty, but when we are further away from points, observed points, so we have some uncertainty, and you see that actually the mean value sometimes makes big mistakes like here. Here are three different acquisition functions, and they try to figure out where we should look for next points, okay? And here how it works, you see that it starts picking points where we will minimize uncertainty. And in the beginning here we had huge mistake, but now after picking these points, it says that, okay, great, we are getting better and better, okay? Bayesian optimization is a very powerful tool. It has some drawbacks. For instance, it goes cubically in terms of number of complexity, grows cubically with respect to number of observed points. So we cannot use too much observations for Bayesian optimizations, but definitely this is one of the most powerful approaches known so far. And at the end, again, from our lab, very specific two tasks, rotation and following an object, and both tasks trained by Bayesian optimization. So following we saw in the very beginning, and as you can see, it is trained pretty well. And now we have rotation, so the robot must learn how to rotate. All right, thank you very much. It's everything for today. So, of course, this is definitely too little about both topics. But again, my point is to teach you that there are such concepts and that you can have a starting point for learning further, okay? That's it. Thank you very much.